See how Taylor series can help us integrate functions. Let J be the definite integral from 0 to 1 of sine of x squared dx. Let me tell you, if you try to integrate this in a straightforward manner and just try to find an elementary antiderivative of sine of x squared, you're not going to be able to do it. This would be very, very hard. So instead, let's write out an infinite series here. Let's replace sine of x squared. Let's figure out an infinite series for that. So sine of x is this expression right here, the sum from 0 to infinity, minus 1 to the n, x to the 2n plus 1, divided by 2n plus 1 factorial. So let's just replace everywhere we saw an x there with an x squared, sum from 0 to infinity of minus 1 to the n times x squared to the 2n plus 1 divided by 2n plus 1 factorial. So x squared to the 2n plus 1, and that's just going to be x to the 4n plus 2. Okay, so now let's go ahead and say we are integrating between 0 and 1 of this sum. We're replacing sine of x squared with this Taylor series, minus 1 to the n, x to the 4n plus 2, divided by 2n plus 1 factorial. And there's some properties here. I won't go into details that allow us to interchange the integral and the sum. So now we have the sum from n from 0 to infinity of minus 1 to the n, divided by 2n plus 1 factorial. None of that has to do with integrating respect to x. So the only thing that's left over is integral from 0 to 1 of x to the 4n plus 2 dx. So when we integrate x to the 4n plus 2, a little bit of sideboard stuff here, integral from 0 to 1 of x to the 4n plus 2. So that would be x to the 4n plus 3. We add 1 to the exponent. We divide by that exponent. 4n plus 3, plug in 0 and 1, and we would end up with just 1 divided by 4n plus 3 minus 0 divided by 4n plus 3. So 1 divided by 4n plus 3. So what do we end up with? We have the sum from n from 0 to infinity of minus 1 to the n divided by 2n plus 1 factorial times 1 divided by 4n plus 3. So here is our infinite series. We have j written. J is this integral. We have j written as an infinite series. We want to write out the first several terms. 1/3 minus 1 over 42 plus 1 over 1320 minus 1 over 75,600 ... But something else we should always be thinking about is just how good is our estimate. Do we stop here? We stop here? Just how close to the actual value of j are we getting? So part B of this problem is, let's determine j to within an error of less than 10 to the minus 4th. Now the thing to realize about j is that we have it written as an alternating series. And so by our alternating series test, there's a couple things going on there. One is that alternating series test would promise us that such a series converges. The terms are alternating. This is positive, decreasing, and going to 0, the stuff that's not minus 1 to the n. But something else the alternating series test does is that it gives us a bound on just how bad, maybe I should be more positive, just how good an approximation can be, just how bad can the error be. So alternating series test tells us that the sum of the first n terms is accurate to less than, accurate to an error less than the n plus first term. So here, so we were asked for error less than 10 to the minus fourth. The term, an absolute value that, this one right here, 75,600, 1 over 75,600, that's less than 10 to the minus fourth. So if we exclude that, this will be to within the requisite error. So what we're going to do is that we're just going to take these terms here. So 1/3 minus 1 over 42nd plus 42 plus 1 over 1320. This is an estimate for j that is within an error of 10 to the minus fourth, because the first left out term changes it by less than 10 to the minus fourth. So you want to know here, this is about 0.31028. So our estimate for our integral j 0 to 1 sine of x squared dx is 0.31028. And j minus 1/3 minus 1 over 42 plus 1 over 1320 is less than 1 over 75,600, which is about 1.3 times 10 to the minus fifth.